if you see anyone at lunchtime, just remember you're meeting here for the prac, not in the other prac venue. There will be a notice there to redirect people, but you must come here. And has everyone got notes? Because I handed out the notes yesterday, and there were a lot left over. All right, so for today, we're going to continue where we left off yesterday, looking at the Witwatersrand Basin. So we're starting with this map again, which I'm hoping is beginning to get familiar. So we've got an outline of modern South Africa on this, but if we were to go back to the Archean times and to the Witwatersrand Basin, we wouldn't have modern South Africa as we know it. All we would have, the only rocks that were around, is this outlined in pink here, which is called the Karpval Craton. And this Karpval Craton is the basement rock that underlies all of South Africa. And a craton is the kind of core part of a continent. So Africa is made up of a number of cratons. North America, Australia, all of the major continents at their heart have these cratons. They're mainly all Archean in age, and they all consist, as we saw in Barberton, of greenstone belts and granites. And these ancient basement rocks basically form the kind of core of South Africa and underlies most of the geology of southern Africa. So here in pink we have our Karpval Craton, and at the time of the Witwatersrand Basin we had rifting on the craton, and so we had a shallow inland sea in the center of this kind of early continent. And this outline here is the rocks that make up the Witwatersrand Basin, but only a small amount. So here we have a blow-up of the Witwatersrand supergroup, and we have the West Rand group, which is overlain by the Central Rand group, and they're shown in orange. And the parts that are grey, so here the greyed out parts, those are where it's mined specifically. And most of these rocks don't outcrop its surface. There's only limited surface outcrops. So much of our understanding of this geology is from the subsurface. And as we talked about yesterday, the major significance of the Witwatersrand Basin is this incredible gold deposit. So we talked about this, more than 40% of all the gold that's ever been mined ever is from the Witwatersrand supergroup. The gold is, we find the gold in the conglomerate units, and these are called reefs. In general, any rock layer that's mined is called a reef. We looked at the basin setting of the Witwatersrand, that it's the shallow inland sea where we've got these various different sedimentary rocks. It's a sedimentary sequence, and it's the coarse-grained conglomerate layers that have the gold. So it's just looking at it again. And this is a cross-section through the basin showing you how today these, yes. So fool's gold isn't actually gold at all, it's pyrite. So pyrite is another type of mineral. It's a sulfide mineral, but it glitters and looks like gold. And in the Witwatersrand, it's associated with the gold. So and it's more visible, there's more pyrite. So it's called fool's gold because it would fool people that it was gold, but it's actually pyrite. So to actually distinguish the pyrite from the gold, they have different chemical compositions. And the pyrite is a more dull kind of color. The gold, is kind of gold. It has a much yellower, richer color. And a slightly different specific gravity, so when the metallurgists come to actually separate them, they can separate out the gold. This is a cross-section looking at the various, just looking at the Central Rand group in particular, and you can see how these layers have all been tilted up. And we talked about how we've got so much gold into this Witwatersrand Basin. And there's basically two models. There's the placer model, and placer is a term that refers to the fluvial transport and concentration of the gold, which is by rivers, and that the rivers were eroding this distant source and accumulating the gold. And then the other model is the hydrothermal model, which is hydrothermal fluids that are rich in gold, and then they come from underground and kind of percolate up, and the gold precipitates out. And we have evidence for gold from both sources, so that's most likely that there's components of both models that have concentrated the gold. So gold was first discovered in the Witwatersrand area, which is Johannesburg today, in 1886, and on Langlaagte Farm. And this is what it looked like. That's a photograph of the Langlaagte farmstead. So this would be central Joburg today. So it's amazing to think that there was, no city. Johannesburg's a young city. And this is what the geologists found at the surface was conglomerate. And as I explained yesterday, the gold has a high specific gravity and settles out into these conglomerate rocks. And it was known that these conglomerates could be gold-bearing. So when they were found at the surface, the rocks were crushed and panned, and there was gold, and quite a lot of gold in them. So this started an enormous gold rush, basically, and people came from all over the world to begin mining the rocks initially just at surface. But very quickly, because the reefs dip underground, they had to start mining underground. And here you can see a headgear, which basically sends, you sink a shaft, and then you have a lift, basically, that goes down to transport people underground to do the mining. And there's a photograph of some miners underground on one of the gold mines from the 80s. So the gold mining has really changed the basically the history of South Africa, and had a huge impact. I mean, that's why we have Johannesburg, and that's why it is where it is. And even the development of Johannesburg initially went out east and west following these gold-bearing reefs. So this is just a simplified cross-section of an example of one mine. So this is Kloof Gold Mine, which is about 60 kilometers southwest of Johannesburg. So this is tracing those reefs around in the more southwestern part of the Witwatersrand Basin. And the amazing thing is, so here in yellow, this is the Witwatersrand supergroup. And you can see here none of it outcrops at surface. We've got the green and the blue and the purple, which are younger rock types, which are overlying the Witwatersrand supergroup, and we will come to talk about them. And you can see the BH, those are boreholes. So these are boreholes which were drilled down up to 3,000 meters below surface to intersect the reefs, so that geologists know basically where to mine. And here you can see where it says number 4 shaft. So this is a shaft that's been sunk down to intersect the reefs, and it's gone down over 300 meters. So South Africa has the deepest mines in the world. And once you sink a vertical shaft, and then you can mine out horizontally to these gold-bearing reefs, and mine out the gold-bearing rocks and then transport them back to surface. So it's an amazing kind of operation. And this mine employs nearly 15,000 people. It's been in operation since the late 1930s and has produced over 250 million megatons of ore, which equates to 70 megatons of gold. So it's just an example of kind of just looking in detail at one mine. Yes. Not exactly. So all of the yellow part is the Witwatersrand supergroup, where we have different rock types, and it's only the reefs, it's only the conglomerates that have the gold in them. And the whole of the Witwatersrand supergroup isn't conglomerate. We have sandstone, we have mudstone, and it's just the conglomerate layers, and they're marked here. And it's just every now and again in the succession of rocks you have a conglomerate layer, and that's where the gold is. And pretty much without fail, the conglomerates have gold in them. So those are the reefs, and that's what the mine is targeting. And you can see over here that it's not a perfect sequence. You can see how they've been tilted, and then here you have enormous faults where the sequence is being faulted up. So it's all a bit more complicated than the kind of textbook example of rocks forming nicely in a sequence. Then this is another aspect of the gold mining around Johannesburg. So this is a photograph from the south looking up towards Johannesburg. There's the CBD. And a really iconic part of Johannesburg's landscape are the dumps, the mine dumps. And this is from where particularly the early mines, the gold was extracted out of, or the rock was mined out and crushed and brought to surface, and then the gold was extracted out. And you have a huge amount of waste rock, which was basically just dumped and formed these enormous mine dumps. And this has been ongoing since the late 1800s. So these enormous mine dumps are really part of the kind of landscape of Johannesburg. But since those early days, the extraction, the metallurgy has really improved, and we have much better methods of extracting gold. And when the gold price is high and it's really cheap to actually mine these mine dumps compared to mining underground, because the gold underground is getting deeper and deeper. So you could think a shaft 3.5 kilometers underground, it's all very expensive and very kind of complicated, or it could actually recycle these mine dumps. And you can see this one here, which is just south of the city in Johannesburg, and the city's kind of grown around it, and it's actually been mined away. So we have a little video to look at this process.
For thousands of years, gold has been one of the measures of wealth. The Incas, Romans, Egyptians all knew its value. They dug deep for their wealth, but this gold is a little different. It's actually been sitting on the surface in plain view for years. The waste material from mining stacked high around South Africa. This little dot of gold is about 0.3 grams, and there's about this much gold in every ton of waste material. It doesn't sound like much, but consider this. There's about 140 million tons of waste material at this single dump site alone. At today's gold prices, that's about $2.2 billion worth of gold already on the surface, lying out under the sun. This waste recycling of sorts begins with water cans cutting like lasers into the piles, washing the waste into a pipeline. Then it's pumped to a treatment plant and mixed with chemicals to extract the precious metal. The technology isn't new, but the high price of gold means it's now well worth the effort.
We believe the gold price is going to continue going up, and that technology is going to continue improving. So it does open up a lot of scope for us and potential to be able to treat a lot more of these mine dumps for a long, long time to come.
Even after all of this, there is still some residual gold left in the waste material. When the time, or rather the price, is right, it could be reprocessed again. Tanya Page, Al Jazeera, Johannesburg.
Okay, so that was just kind of showing how this, it's an ongoing process, and there's always new research and new efforts kind of, it's not a static process. All right, so moving on from the Witwatersrand supergroup, we're now going to look at the next supergroup. So we're going up through our geological timescale, and we're moving up to around 2.7 billion years ago to the Ventersdorp supergroup. And this is a supergroup characterized by basaltic lavas, so a period of major volcanism, basically. So here we have the map, which, as I said, I hope is becoming familiar. So we have the outline of modern South Africa, and we have our Karpwal craton sitting here, and we've got the Witwatersrand supergroup, which basically that shallow sea has been filled up with sediments, including the gold-bearing conglomerates. And at around 2.7 billion years ago, the Witwatersrand supergroup time ends as this Karpwal craton, which is sitting here, collides with the Zimbabwe craton. So the Zimbabwe craton is similar in composition to the Karpwal craton. There's greenstone belts and granites. And because of the plate tectonic processes, these two cratons collide. And it would be similar to it's similar to what we see today, where the African and Asian cratons are colliding and produces the Himalayas mountains. So that's what's happening, and why we have the Himalayas, are these two continents basically colliding and forming a mountain belt. So we have a setting which is similar here, but 2.7 billion years ago, where the Karpwal craton and Zimbabwe craton collide, and we had an enormous mountain range up here, the Limpopo mountain range. And basically, because of this collision, we have enormous rifting and volcanism on the Karpwal craton, and this enormous outpouring of basaltic lava. And this huge area of South Africa was covered in these basaltic lavas, which basically filled up and sealed off the Witwatersrand basin, which preserved the gold-bearing deposits underneath. So yeah, here's some text saying what I was just explaining. So it was a Himalayan-type mountain range, would have been built as the two cratons collided. this impact would have caused rupture and enormous rifting in the interior of the Karfol craton, and huge volumes of these Fenterstorp lavas poured out at surface. So over a kilometer of lava would have poured out, and we believe about 6 million years of eruptions. And this is a photograph. So this is south of Johannesburg. Yeah, the lights are a bit bright. So this is from the south of Joburg looking up, and you can see the TBD. And all of the southern part of Johannesburg is all the rocks that these houses and everything are built on, are all these basaltic lavas. And another place where we see the basaltic lavas at the surface is in Kimberley. So this is where the big hole in Kimberley, which is a diamond mine, and we'll talk about much later. But the solid steep cliff above the water, so this part of the hole, what's exposed here are these Fenterstorp lavas. So that's just to give you an idea of the extent of the lavas. They covered the area from Johannesburg to Kimberley and even more. So it was an enormous volcanic event. And during this time of the collision of the Karfol and Zimbabwean craton, we had this enormous mountain belt, but then eventually this has been eroded just through kind of natural processes, and what we have left in between where these two cratons collided is called the Limpopo belt. And that today, the erosion of these mountains and the erosion of the area between where these cratons collided has brought very deeply buried rocks to surface. So today the Limpopo belt, which is still exposed at surface as this kind of suture zone between the two cratons, and they're highly metamorphosed rocks. And this is quite a typical pattern that we see between cratons, and the cratons are kind of stuck together by these metamorphosed mobile belts, and the Limpopo belt is an example of that. And then so we have the Fenterstorp lavas at about 2.7 billion years, and then a billion years later we're looking back at the craton, and things have begun to change again. The craton is still being rifted, and we have the flooding of a shallow sea invading from the west, and there's more rifting across the craton and some more volcanism, but much more restricted. And at about 2.6 billion, the whole craton floods, and we have another shallow sea and the deposition of the Transvaal supergroup. And the Transvaal supergroup we're going to look at in more detail next week, but this is just basically the setting of it. And now it is time for a quiz. So I did tell you we were going to do some in-class quizzes, and this is not for marks, it's just to see, it's basically a test for yourselves to kind of see how you're going. So I've got some quiz sheets here, we're going to hand them out. We've got 20 questions, and I'm going to give you 10 minutes. They're one-word answers, and then we're going to mark it in class. It's not for marks, it's not too serious, it's just to see how you're going and if you are listening to me. If you should be paying more attention. All right, you can just pass them on. No, I think it's better if you don't use your notes. I mean, it's for yourselves to see how much you're taking in. Here we go. You can take one and pass them on, please. Okay, so when everybody's got one, I'm going to give you 10 minutes to answer the questions. Okay, time's up. So now, I want you to swap with the person next to you, and we're going to mark it together. Now this is a safe space, be nice to your friends. And it's just for your own, it's just to see how you're going. So swap with your friends. If you don't have, Make a plan, swap with your friends. Be nice to each other. Okay. So, all right. Question number 1. The relative dating of geological events relies on whose laws? Steno. Yes. Nicholas Steno. Steno. Okay, so Steno, yeah. That's fine. That's fine. Steno, I'll take Steno. Okay, guys, come. Shh. Let's do this together. Okay, question 2. The principle of superposition. Yes. Okay. Yeah, I've got the answers here. All right, so question number 2. Come on, it's back. The principle of superposition states, A, a sequence of rocks gets younger from top to bottom. B, the oldest rocks are at the base. Well, the problem is now you can all see the answers. Yeah, I think it's better if we go through it without seeing the answers. I'll put them on ruler tonight, okay? So, yeah. B, the oldest rocks are at the base of a sequence, or C, the rocks in the middle are older than the rocks at the base. B, well, yeah, you should all get B. You saw the answer on the board. So a sequence of rocks gets younger from so from the bottom to the top it gets younger. And the rocks in the middle of a sequence are younger than the rocks at the base. Okay, so using fossils preserved in rocks to order or date them is called? Yes. Biostratigraphy. So the eons. So eons are the longest units of geological time. They're the major things that the geological time scale is divided up into. So the eon before the Archean, the very early Earth, is called the Hadean. Yeah. Hadean. Hadean. Okay, so the Phanerozoic is divided into 3 eras. Name the eras of the Phanerozoic. Yep, Cenozoic. I'll take Cenozoic. Mesozoic. Yep. Paleozoic. Yep. So the oldest is the Paleozoic. Paleo means old. Mesozoic is the middle era, and Cenozoic is recent. Okay, absolute dating relies on what? Radioactivity. Yeah, radioactive isotope. So I'll take radioactivity, radioactive isotope decay, isotopes. How are your friends doing? Be nice, be generous. Okay, so name one of the 3 types of radioactive decay. We've got 3 types of radioactive decay. Yeah? Yep. Alpha, beta, gamma are all types of radioactive decay. Don't laugh at each other. It's not nice. This is why you're not marking your own one. Okay, so now uranium decays to ultimately, yes, lead. Nice one. 206 lead. If anyone got 206 lead. Bonus marks. Okay, name the most useful mineral for uranium series dating. The most useful. Zircon. Yeah, zircon. Yeah, zircon. Z-I-R-C-H-O-N, zircon. All right, how old is the Earth? Yes, 4.6 billion. Okay, what material is suitable for carbon dating? What can we date with carbon dating? Yes, organic material. No, you can't say fossils, because lots of... No, a fossil, the organic material's been replaced and they've been fossilized, and they're often replaced with silica, so they've actually become inorganic. So, no, you can't have fossil. If the bones are young enough and haven't been completely fossilized, you can date them with carbon dating, but then they fall under the kind of umbrella term of organic material. So if someone's got bones, okay, give them half a mark. All right, the earliest traces of life preserved in the Barberton supergroup are called, stromatolites. Remember we had the nice Australian lady in the video telling us about stromatolites. Yeah, exactly. So the cyanobacteria form the stromatolites. So that's fine. Yeah. Nice one. Well remembered. Okay, so the rocks of the Barberton supergroup are collectively known as the rocks that we saw in Barberton were collectively known as greenstone. A greenstone. Okay, what is special about composite lava? Oh yeah, the spinifex texture. Yeah, so it has a spinifex texture, but I guess what I'm really looking at, there's something really, so spinifex texture is good, but there's something really specific about it that's different from lava that we have today. Yes, it's very hot. Yeah, it was much hotter lava, and it was from the mantle, so it's a mantle-derived hot lava. It's very hot. It's a much hotter lava than we get today, up to 500 degrees hotter, which is all to do with the Earth being hotter in the Archean. All right, so what is the name for basalts that erupt underwater? How would you tell? Yeah, pillow basalts. Pillow basalts. And they have those pillow-like structures that looks like toothpaste being squeezed out of a tube. Okay, so true or false? Stromatolites live in deep water. Yes. Yes. Stromatolites live in shallow water because the cyanobacteria have to photosynthesize, so they need to be able to see the sunlight. And so they're actually an indicator of shallow water conditions. If you find stromatolites, you know the water had to be shallow. Okay, name the ancient basement rocks underlying much of the geology of South Africa. Guys, I say this over and over again. Yes. You're warm, yeah? Yes. The Karpval craton. So this was actually an exam question last year, and I cannot tell you how badly people did on it. And I was just about crying because I was like, I've said this every lecture. So the basement rocks of South Africa, which consist of the greenstone belts, Barberton is just one example, the various greenstone belts and the granites, which stick the greenstone belts together. And this forms a craton. And this craton is the kind of core of the continent. And the craton that underlies, and is the core of southern Africa, is the Karpval craton. So it's called that because Karp and Val, it's underneath the Cape and what used to be the Transvaal. So that's where the name comes from. It's like the Cape Val craton, Karpval craton. And if you, it's the kind of one take-home message of the geology of South Africa, that almost all the basement rocks in South Africa is this crystalline basement, the Karpval craton. And the important thing about the Karpval craton is that it's old, it's Archean, and it's this old, cold craton, which is important when we come to diamonds. And these cratons are also associated with gold. So it's a lot of the geology of South Africa all links back to the Karpval craton. Okay, the Witwatersrand Basin is famous for what mineral? Yes, we just did that like half an hour ago. What type of rock hosts this mineral? Where do we find the gold? Yes, in the conglomerates. And what sparked the eruption of the Ventersdorp lavas? What was happening that we got the eruption? Yes. Yes. So the collision of the Kafal and Zimbabwean craton caused the major rifting, you were going to say that, on the Kafal craton, and we have the enormous volcanism. And the Ventersdorp lavas then seal off the Wits Basin. Okay, so you can add up the marks. It should come to something out of 20. Be nice, they're your friends, this is a safe space. And give the marks back. So as I said, guys, this is not for marks, it's just to give you an idea of kind of where you're going. Yes. No, I haven't totally decided, but the 16th is a public holiday, and I think I'll do it for the long weekend. So you guys have some work on the long weekend. Okay, so I'll put the quiz and the answers up on Vula so you can have a look. And yeah, this is just to give, and in the exam there will be a section similar to this of like one-word answers. So this is just giving you a taste of what you should be absorbing from the lectures. So that's all we're going to do today. We'll continue with the Transvaal Supergroup next week. And remember to come back here for your prac this afternoon. All right, thanks guys. Yes, I think over the long weekend, the 16th is a public holiday. Not this weekend.